All right. In today's program, I'm going to talk about the Dickey-Fuller test of unit roots. Okay, in a time series. All right. I shall talk about the Dickey-Fuller test of unit roots. Okay. All right. So the topic for today is Dickey-Fuller test of unit roots in a time series. Okay. All right, but we are supposed to at least know the main idea of the Dickey-Fuller unit root test. Okay. In statistics, the DF, where D represents Dickey, while F is where F is what? Fuller. So I said in statistics, the Dickey-Fuller test is a unit root test okay, which shows whether an R model or autoregressive, which shows whether an R model or autoregressive model of process of order P follows of order P follows a random walk. Okay, so like I said earlier, let me repeat myself again. I said that in statistics, the Dickey-Fuller test, that is DF, is a unit root test which shows whether an autoregressive model of order P follows a random walk or not. Okay. Full stop. All right. The test was developed by David Dickey and Dickey-Fuller at the demise of the 70s, or simply in the late 70s. Okay, so all right. So I said that the test was developed by David and Dickey-Fuller in the late 70s. Okay, mind you, the David is David Dickey, okay, and Dickey-Fuller. Okay, so the test was developed by David Dickey and Dickey-Fuller. All right. So, Dickey-Fuller, full stop. Okay. We shall look at the main idea of the test. The main idea is to test the null hypothesis that there is a unit truth. Okay, so I say the main idea is to test the H sub 0, that is HO, that there is a unit root, and that is beta equal to 1. Okay. All right. Against the alternative hypothesis, that is the H sub A or H1 hypothesis. H sub 1 or sub A, okay, that there is no unit root. There is no unit root. That is beta is different from unity. Alright. If the HO is accepted, then it means that there exists a unit root, meaning that the series follows a random walk. And whenever a series follows a random walk, that series is said to be what? Non-stationary. And the error term, epsilon, is a white noise. Okay? So that if the null hypothesis H sub 0 is accepted, then it means that there exists a unit root, which means that the time series follows a random walk. Full stop. Okay. All right. But if the HO is not accepted, then it means that we have to accept the alternative hypothesis, that H sub 1 or sub A, that there is no unit root, and the series does not follow a random walk, meaning that the series is not what is already stationary. Okay, so suppose the alternative hypothesis, that H sub 1 or sub A, is sorry, I said suppose the null hypothesis is not accepted, meaning that it is rejected. It's not accepted. Okay, meaning that it is rejected. Then we have to accept the alternative hypothesis, that H sub 1, that the alternative hypothesis H sub 1, that there is no unit root, meaning that the series does not follow a random walk. A random walk. First up. Like simply, whenever a series does not follow a random walk, it means that the series is non-stationary. Sorry, please. Whenever a series does not follow a random walk, it means that the series is already stationary, or is simply stationary, because our h sub 0 is not accepted, rather rejected, while our h sub a or sub 1, which is the alternative hypothesis, is accepted. Okay. Again, it should be noted that a series which follows a random walk is non-stationary, as said earlier. Like I said before, okay, while a series that does not follow a random walk is said to be what? Stationary. Okay, we shall use our algebra to show the Dickey-Fuller unit root test. In this case, I shall use a dynamic model. An example of an instance of a dynamic model is an R model, that is autoregressive model. Okay, let me say the first order autoregressive model. Okay, the first order autoregressive model is given below. That is, and in this case, we shall call this the simplest autoregressive model. That is the first order autoregressive model. That's an R of 1. Okay, an R model of 1. Okay, so we have our first equation, that is the time series, okay, where we have y sub t equals, let me say, beta, then the first leg of the y sub t minus 1. Okay, plus the epsilon, where the epsilon stands for the error term. We call this our first equation, and our first equation. Okay. All right. So we should solve. Our main aim here is to see actually if our unit root will become, well, one of the values of our characteristic root will become unity or 1. Doing that, let us subtract the first leg of y from both sides. We said that let us subtract. Okay, now let me say subtract the first leg of y from both sides of the equation. That is beta y sub t minus 1. If I'm to subtract from both sides, I shall obtain a new equation. That is my equation 2, which is y sub t minus wait. Okay. So no. Now there's a mistake. Let me just get it corrected. Okay. All right. T minus 1. Okay. So doing that, I have my y sub t. Okay. Minus beta times y sub t minus 1 sub t minus 1 equal to the epsilon sub t, that is error term at time t. Okay, recall that the first leg of y, that is y sub t minus 1, is the same as the first leg of y at time t. Is same as the first leg of y at time t. Okay, sorry, I repeat again. Recall that the first leg of y, that is y sub t minus 1, is equal to, okay, L of y sub t. Okay, so from the second equation, that is our equation 2, okay, I substitute in place of beta times y sub t minus 1, in place of y sub t minus 1, I shall put ly sub t, meaning that it is the first leg of y. That was, this is the equation to y sub t, oh, sorry, that was, this is the equation to y sub t minus beta first leg of y sub t equal to the error term at time t. Okay, so we have obtained our third equation, so we label it our third equation. Okay, let me factorize. Okay, just factor out the common factor, or just factorize. Alright, we factorize to have y sub t of 1 minus beta L, 1 minus beta L equal to epsilon at time t. Okay, so this is our equation 4, our first equation. So we are getting to the end of the program anyway. So now at this point we create the characteristic root, or let me say characteristic equation. Okay, alright, this is done by setting the coefficient of y sub t from the left hand side of equation 4 equals to what? 0. Okay, doing that we have 1 minus beta L equal to 0. Okay, so now we shall solve for L. Now at this point we say let L becomes Z. Let L becomes Z. So we have 1 minus beta z equal to 0. Okay, so at this point I shall solve for the simple linear equation, and here the variable here is z. We know that the beta is a coefficient, a non-number which is different from 0. Okay, so solving for z, I transpose minus beta z to the left hand side to obtain 1 equal to beta z. Okay, now I divide through by beta to have 1 over beta to have 1 over beta equal to z. Okay, so like we said earlier, that beta must surely be different from 0, so that we have a defined function. Beta must surely not be equal to what? 0. Okay, so that makes us to have. So if beta is equal to 1, then we have our root to be z equal to 1. We have our root to be z equal to 1, because if in case of z equals to 1 over beta and beta is not 0, in this case beta is equal to 1. If we substitute 1 in place of the beta, we shall have z equals to 1 over 1, and 1 divided by itself is still 1. So in this case, we accept the null hypothesis HO that there is a unit root. So in this case, HO is accepted. Okay, accept HO, accept. Okay, HO is accepted. All right. In this case, there is a unit root, and the series follows a random walk. Okay, and the error term epsilon is white noise. The R model is non-stationary. Okay. So conversely, if beta is not, or is different from unity, is not equal to 1, okay, then we say that the series is stationary. The series is stationary since it does not follow a random walk. Series is stationary, okay, since it does not follow a random walk. Okay, at this point z is different from unity. At this point z is also different from unity. That is, z could be higher than unity or less than unity. Whichever the case is, it shows that the series does not follow a random walk, and the time series is non-stationary. All right. Thank you so much. Hope this helps. Bye. Makasi Chinedu. Thank you.